So hello guys, welcome back. Today I'll be discussing the spinning top, just the top that we generally play with, and the two situations of precision and nutation. And I'm gonna not go into details of how to derivate formulas basically for the different motions, but why it basically happens was what interested me the most when I was learning it. And I will be telling you, like explaining in this video, what I understood of them and basically my recollection of the things that happened at one place. I would have loved to have such a video back when I was studying because I also had some difficulties in actually understanding why nutation takes place. But I hope through this video I can make it a bit clearer. I have, of course, taken help from some books, which I'll be linking again in the description. And I hope the video helps you guys. Um, so, without further ado, I'll be going through. The first thing that we'll be discussing right now is precision. So, precision, I am writing it in the German one, sorry. So, precision is, I have also made like a sketch of it already, so I will just add it here. So what you see here is that like a top, it is rotating on its own axis with like its own figure axis. It's one of its own symmetry axis with an omega. You have the figure axis of the symmetry axis with a vector of f, and then you also have the like basically the spin moment L, like the and the spinning and the like the angular velocity of the precision is omega p, which is of course different from the other omega that we have on its own axis. Then you have a phi. Basically, it is inclined from its previous symmetry axis, previous axis of rotation by an angle of phi. And what actually happens is that in during precession, the top, it basically moves in like its own axis of rotation. It basically moves along another axis of rotation, and that is what we call precession. Earth also has it during its own rotation, like its own rotational axis also rotates around another axis, and we call it precession. But this basically happens because there's a force that is acting on it, and you have here, so in this diagram you actually have an r, like a position vector of the force F, which is basically denoted here by a mass of m which is hanging, and you have a force of mg which is at a position vector of r, which of course this thing also has like a angle of phi, mathematical rules. And then what actually happens is that when you have a force, you also have in angular motion something called a torque. So a torque is basically r, so the position vector cross the force vector, and this is basically what gives rise to the precision. So to say, let's make it in a different color. So if you have the r and the f, when you basically do a cross vector, you get another finger that's pointing inside the plane we are watching right now, so inside, and that is exactly what spins the already spinning top into another axis of rotation. And so this is why basically precision happens, and it is because only when there is a constant constant force working on the body, on its symmetry axis, on the axis that it is already rotating about. Now, before we go to nutation, we also got to define some terminologies before, and we have, of course, the first, the angular impulse, which is equals to the moment of inertia tensor, and the vector which defines the angular velocity. So you have this, which is again a very important formula, and this in vectorial terms would obviously look something like this, where the angular impulse has three components in the Cartesian coordinates, and then the tensor obviously has, it's a 3 into 3 if it's a 3D thing, it's a 3 into 3 matrix, with many of its elements inside the matrix, and it all is basically a part of the moment of inertia tensor. Then you have the omega. The omega has also 3 components. So this is basically how this formula looks like in the vectorial form. And now you have to understand that there are, of course, some forms of coordinate axis. When we have a top like this, again, my drawing skills are pretty bad, so sorry for that. You have like a top is rotating like this, and then you basically tilt the top in this plane, in this angle, and then what happens is basically you have two kinds of coordinate system. One is where the coordinate system stays true to the room, and the other one is when the coordinate axis basically bends according to the body. So the first one is called the room or the space coordinate system, and the second one is the body coordinate system. So I'll be using R for room and B for body coordinate systems. And there is a formula, I will not go to the derivation of it, but there is a formula in which you can actually convert the torque from one to the other. And that is basically this formula. The torque of a room based, like a room fixed coordinate system, is basically equal to the torque of a body coordinate system plus the angular velocity cross, like the cross vector, the angular moment of the body also. So, and what is torque? Again, torque is the change of L in time. So you have dl of the room dt is equal to dl of the body dt plus omega cross lb. So this is what we are working with. This is what we are working with for nutation. This is a very important formula that we will also get to know. So once we move to nutation, it is a bit different because nutation is where the angular momentum does stay conserved, and we'll talk about that in a moment. When you saw in precession, the angular momentum was actually changing with time because of the torque that you have here, because of the force that you have here. So the L was indeed changing, but the change was constant for a constant force. But for nutation, you have the angular momentum which is actually conserved. So the first case is when the angular momentum is actually conserved and you do not have any kind of external torque. So basically the torque is zero, so there is no kind of force. Force is also zero. So what happens is that L dot is also zero, and that means L is conserved in the system. L is conserved in the system. This is very important because now let's say when we have a top like this, and we have the symmetry axis, we have the angular velocity axis, and we have the L all showing in the same way. And what you basically do is you give like a push in its symmetry axis, and it kind of just bends a bit. Then of course if you have your coordinate axis defined like this, you can say that when you give it a slight push on one of the sides, what was before only Lz before now also has, like, so basically the L has now two other components, Lx and Ly. Now this is of course a problem because the Lz is basically conserved because the push on the side gives it an additional L on x and z, x and y. So what basically happens is that the L changes a bit, and in this system, because there is no constant force acting from outside, you cannot have a change of L. So the system has to somehow conserve L. And again, as I said, since t is equal to 0, as we saw. So L has to be conserved. So this must be 0. It has to be conserved. So now if we go, let's go for the Euler's equations. If we look at the Euler's equations for these, so for the 3 coordinate axis, it will be Tx. So the torque in the x axis will be equal to, again, the IA. I also forgot to introduce the IA because this was like the I thing, like the moment of inertia. It also has its own eigenvalues. So the eigenvalues of I are basically the symmetry axis of a body. When we are taking a top, let's say a top in this case, then we have the IA and IB as constant, but the IC is not, because one can see when you rotate it about this axis, so the x-axis and the z and the y-axis is basically the same because the mass distribution is the same, and the radius is also same. But when it rotates about the z axis, it has a different way, like a different radius, and that is why the IC is of course not same. So we can also of course say that these are like these constitute like IX, IY is not equals to IZ. But I'll be considering them IABC because, well, I've learned it in that way, so it's better just to keep it that way. If you also are not accustomed to it, so you can just change it in if you want. I'll try to keep it in that way. And basically what happens is that in this case, when you only have the symmetry axis, and believe me, all bodies have coordinate systems in which you can write the moment of inertia only in the symmetry axis, then in that case, these elements will be 0, and there will be only elements in these, the diagonal elements basically, which you can diagonalize and everything. Wouldn't be going to that much of a detail. But what you can basically see is that now if we use the Euler's equations, so this is like a side note. If we go now for the Euler's equations, we see that the x component of torque will be Ia d omega x dt, so the time change of it, and then the IC minus IB omega z omega y. Then you have torque of y is equal to IB d omega y dt plus IA minus IC omega x omega y. And then you have sorry, this will be omega x omega z, my fault. Then you have the torque of z, which is IC d omega z dt plus IB minus IA omega y omega x. Exactly. So now when you think about it, since IA and IB are the same, we can basically, I will reduce my eraser, like the radius of eraser a bit. So what you can see is that IB and IA, I'll mark it once again, they are same. So you can basically remove this IB and write it as IA. You can remove this IB and write it as IA, and everything basically stays the same. But what we can also do here is we can turn these on one another, and then it will be IC minus IA with a minus outside. So we basically bring the minus outside, and this is how the equations now look like. Why I made those changes will be clear in a bit. So what we see right now is, since also IB and IA are similar here, this basically becomes 0. So how the things also look like, because also like the torques are all equals to 0 because we do not have any external torque, the equations will look something like 0 is equal to d omega x dt a plus IC minus IA omega z omega y, and then you have 0 IA d omega y dt minus IC minus IA omega z omega x, And then you have 0. Since this is already 0, we have IC d omega z dt. Right. So what you can do here is that, of course, you can see that the IC can be brought on this side, and basically because IC is never 0, we can always bring it on the left side. And what we can write here is basically 0 is equal to d omega z dt. But for these other two, we can, of course, divide them by IA. We can divide them by IA. And what we get is 0 is equal to d omega x dt plus IC minus IA divided by IA omega z. I will put this in a bracket. Sorry, I was a bit quick in that. Omega y, and you have 0 is equal to d omega y dt plus, you have the, sorry, it's a minus, IC minus IA divided by IA omega z omega x, and then you have the 0 is equal to d omega z by dt. These two, as you see, are the same here, so you can call them bigger omega just for simplicity. And what you see is that there are three differential equations in this case. So of course the third one is kind of understandable, since it is 0, it is conserved, it's a constant. But the other two, when you solve them, I will not solve it right now in steps, but what you basically get as an answer is that omega x, omega y, omega z, I will write them in vector forms, are for any amplitude a cos omega t, a sine omega t, and a constant c. So what you really see here is that the x and the y components of the angular velocity is basically explaining a circle. It is basically like a movement in a circle. So what basically happens is that if you look at the top from the, so this is the top from the top. So like we have this is the x, this is the y, and you have the z coming out. Coming out. Then in that case, we have a movement. When we push it in this way, we have a movement in this region. And this is exactly a circle equation that is defined through exactly these two components here. These are circles. So this is exactly why the nutation happens, because the L has to be compensated with the movement of the direction of omega x and omega y. Now this is the case in which there is no constant force acting outside. So what if you have a constant force? What if you have a constant force acting on it? So there is a torque, so you have a precession, and then you also have a nutation on top of that. So in that case, the differential equations that you saw here, since these had 0 on the left side, these are homogeneous differential equations. But if you have now a precession, what basically will happen is that something like this, a constant, let's say, will come out on the left side. So you have d omega x dt plus, I'll just not write the whole thing again. I'll just write the bigger omega, smaller omega y, and then you have big Y d of omega y dt plus bigger omega x, and then you have also the z is equal to d omega z dt. What basically happens here is that you have like basically the values for omega x, omega y, and omega z here will be a bit different, but it will be still a nutation. It will be still a nutation that is conserving the angular momentum. So the angular momentum, angular impulse, or however it is called. The L, I'm very bad with the English terminologies of them because I mostly learn them in German. But what I basically want to say is that it is also conserved. So in precession, even though like conserved well is a bad term in this case because you already have a torque acting on it, but it basically stays the same. Like you cannot, like the value of it basically stays the same, because In that frame, in its body frame also, body coordinate system also, it is conserved, if you think of it in that way. So yeah, we discussed the reasons for precision and the two forms of nutation. I hope I could bring my point to be a bit clearer to you, and I hope I could somehow explain the whole situation a bit. So if you like the video, drop a thumbs up, comment if you find any kind of errors in my calculation or anything that you would like to be added to such things, or any future videos that you would like to have in my channel. So, and of course subscribe if you want more of such videos. I would be really happy to explain. I would find time from my schedule and I would surely explain. I also want people to do that for the love of science, so I would also do it. And exactly, so till next time, and I really hope this helped. Bye bye.